Alright, so today we're going to talk about isosceles and equilateral triangles and how their properties relate to solving for different sides and different angles. So the isosceles triangle theorem tells us if the two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So for example, if I have this triangle right here, there's triangle A, B, C. And AB and BC are both congruent sides. So AB congruent to BC. What this is telling us is that the opposite angles, the angle opposite AB is angle C, and the angle opposite BC is angle A. Again, notice the tick mark is pointing towards the angle. Also in a triangle, if we have AB, what's missing? C. There's my opposite angle. If I have BC, what's missing? A. There's my opposite angle. We use arcs to signify congruent angles. The converse is also true if you're given the two angles are congruent, and that will mean the two sides will also be congruent. Just pause for a second. Now, in addition to these two theorems for isosceles triangles, we need to talk about equilateral triangles. Now, these are very trivial problems. If all three sides have the same length, they're all equal to each other, that means all three angles are also equal to each other, and then they all will be 60 degrees. They're 60 because the entire triangle adds up to 180, and since all three angles are the same, 180 divided by 3 is 60. The opposite is true. If all the angles are all equal to 60, then it means all three sides are the same length, whatever that number is happen to be. Now, two special isosceles triangles that come about from this situation are this. If you have an isosceles triangle, meaning you have two sides equal, and one of the angles is 60 degrees, then all angles are 60 and all sides are equal. Therefore, it's equilateral. If you have an isosceles triangle where two angles are given, and both those angles are given to you at 60 degrees, again, all three angles are 60, and all three sides would have to then be the same. So pretty much, if you have an isosceles triangle with 60 degrees, they're really equilateral triangles. Similar idea, if you have a right isosceles triangle, meaning you have your right triangle, two sides are equal. One angle is obviously 90 degrees because it's a right triangle. The two acute angles, the other two angles, will both be 45 degrees. They have to be the same. The whole has to have to 180. That's why they're 45. So we're going to use these concepts to solve different problems for X, Y, and Z. Alright, so this first one, we have this triangle right here. So two sides are equal, so it's an isosceles triangle, but one of the angles is 60. So that really means this triangle is really equilateral. Since it's equilateral, all angles are equal to 60, so to solve for X, we would say 10x minus 7 equals 60 degrees. So we add 7 to both sides. 10x equals 67. Divide by 10. X would either be 67 over 10, the fraction, or 6.7, the decimal. Both are acceptable. So here's an example of an isosceles triangle with one of the angles being 60 degrees. Here we have another isosceles triangle, and it's a right isosceles triangle because of the right angle. Since it's a right isosceles, both these acute angles are equal to 45. So we can say 13y minus 7 equals 45. So we add 7. 13y equals 52. We divide by 13. This one's nice. Y comes out to be 4. So those are two examples of your special isosceles triangles. Now, not all of them will be like that, but there's two perfect examples of what to look for. And here's another one. We have an isosceles triangle because two angles are both 60. But, as we said before, since both angles are 60, really the third angle is also 60, meaning all three are the same, meaning all three sides are equal. So to solve for X, I can say 2 to the 3x minus 2 equals 32. So in order to solve for this, I need to have the same base. So I need to rewrite 32 as 2 raised to some power, and 32 is 2 to the 5th power. So the exponents are now equal. So 3x minus 2 equals 5. Add 2. 3x is 7. Divide by 3. And x either equals 7/3, the fraction, or 2.3 repeating the decimal. Both are acceptable. So don't forget your different rules for solving exponential equations. Now this one gets a little bit more interesting. This is an isosceles triangle, but it's not one of our special situations. And we have two variables. So while it would be true that these two angles, 9x plus 5 and 3y minus 12, are both equal to each other, we can't use that to solve because I don't know one of them yet. I instead need to use this concept that this is 74 degrees and these two angles have to be the same measurements because they're the two base angles. Here's how you find the two base angles when you're given this middle angle right here, which is not equal to anything. You're always going to do 180 minus that middle angle divided by 2. Because in this triangle, if we consider these two angles z's, z would be z plus 74 is 180. So 2z equals 180 minus 74, 106, divided by 2, and that's 53. And that's what we're doing here. 180 minus 74 is 106. That divided by 2 is 53. So these two angles are both 53 degrees. So to solve for x, 9x plus 5 equals 53. When you work that out, you will get x to either be 16/3 or 5.3 repeating. For y, 3 minus 12 equals 53. When you work that out to solve, you should get 65/3 or 21.6 repeating. So this is how you solve an isosceles triangle where you're not given the two angles right here. All you're given is this middle angle right up top. It's not equal to either of those two, but you use it to find it. So you're going to do 180 minus this angle and then cut that in half to find these two angles. Alright, so we have another special triangle where these two angles are both 60, therefore the third angle is 60, therefore all three sides are the same. So you can say 7a plus 3 equals 12. You'll get 9/7 for a, which is 1.286. And then for b, we have 8b minus 8 also equals 12. You'll find b to be 5/2 or 2.5. So again, if you have any 60-degree angles, generally the problems will become very nice and very simple. Now this one, leave those 2 marks. This one's a little bit more interesting. So we do have an isosceles triangle, but we don't have any actual angle measurements. This angle is y squared plus 50, this is y plus 5, and this one, we don't know anything about it. Or do we? This angle is the base angle with y plus 5, so we can also consider this y plus 5. So while I don't have any actual angle measurements to solve for y, I can use the fact that all three angles of a triangle have to add to 180. So y plus 5 plus y squared plus 50 plus y plus 5 equals 180. When I combine like terms in this expression, we get y squared, 2y, and 60. That equals 180. This is a quadratic, so to solve we have to subtract 180 from both sides. Y squared plus 2y minus 120 equals 0. We can now factor this. So we set up our two parentheses. So it's y and y to get y squared. The negative 120 tells me it's plus and minus. So I need two numbers, then multiply to be 120, but subtract to be 2. And 12 times 10 is 120, and 12 minus 10 is 2. So that's good. 12, the bigger number, goes with the plus, because that's a positive 2y. So we're going to get two possibilities, negative 12 and positive 10. Now, as always with your quadratics, for geometry, you need to plug them back into check, just to make sure you don't have negative angles or angles that are too big. So we plug negative 12 in first, and for y plus 5, we have negative 12 plus 5, which is negative 7, and no. Can't have a negative angle, so that's not really an answer. We plug in 10. 10 plus 5 is 15. That's okay. 10 squared plus 50 is 150. That's okay. So y equals 10 is my only answer. So make sure you check that and keep that in mind. Alright, so you can use those basic examples to solve different problems similar to this using your isosceles and equilateral triangle concepts. So next time we're going to start talking about congruent triangles and what that means, and then how to write proofs. See you next time.